home. We'll see how it goes. Today we will be talking about the discretization of the heat equation. So to remind you, we got the heat equation by looking at mass balance of density, and it has the form sigma, which is the, you can think about it as heat conductivity, times the Laplacian of rho is equal to the rho dt. And this thing needs to have an initial condition, so we need to know what is the density, where is it sitting in the beginning. So for example, we may have rho of at time 0 and x and y is equal to rho 0. And as we will see, we also need to know something about the boundary of our domain. So we need to know what is rho on, basically, as people write it, as on the partial omega, which means that what happened at the boundary of our domain. And then we can write it as some kind of a function, f. And this is happening rho inside the domain. So you can think about the domain here, omega, and this is d omega, and this is the heat equation which we'll be solving, and that describes the distribution of density in this case over time, and what happened to it when I start at a certain density. For example, let's say there is a density here. What happened to the density as time goes by, and where does it go to? And that's what we'll be doing right now. We'll talk about discretization and the numerical solution to this, and it will accompany with a Python notebook that you'll be able to program and do some things with. Talking about solving or discretizing this equation by few pieces. And I will start by really thinking about the Laplacian here and how to discretize the Laplacian. So to recall, the Laplacian of rho is really two derivatives. It's d square rho to the x square plus d square rho to the y square. Now, the way we're going to discretize this, we're going to just be thinking about our domain is not going to be any shape, it's going to be a rectangular shape. So we'll think about some kind of a rectangular domain over here. And the way to discretize things is to just put grid points or to put a mesh. And the mesh is just going to be, in our case, a very simple mesh. It's going to be what we call a uniform mesh. So there'll be cells. And to make things even simpler, we'll make them even, well, cubical cells. They don't have to be cubical, but we make it the discussion right now to make them even, which mesh size h. So you can think that I have n cells of these, and maybe m in the other direction of mesh size h. And now I need to decide where I'm discretizing my rho. So I would put rho, in our case, in the cell center, I have two options. One is to put them in the nodes, and the other one is I have an option to put them in the cell center over here. And we will actually put them in the cell center for some reasons that we will discuss later, but it's not really that important. If you want to put them in the nodes, in principle, you can do that. So now comes the question, how do I discretize this equation? How do I write an equivalent operation to the second derivative for the Laplacian of rho on a grid like this? So first thing, I need to come up with notation, and the notation would be that I have, if this is pixel, so I'm going to use the simple notation that this is going to be 1, 2, 3. So in some way, this is our x direction, this is our y direction. And rho ij will be rho at point xi, yj. That's my notation to kind of look at this particular thing. So now I need to look at derivatives both in x direction and derivative in y direction. And we have seen, and you guys have worked on it, that it's actually simple discretization of the derivative in the x direction, for example. We've seen this. It's just taking the following approximation. You can think about that d square rho to the x square is just going to be approximately equal to a rho at point I plus 1j minus 2 rho ij plus rho I minus 1j. We've seen this in our over h squared. We've seen this in our first module when we learned about finite difference and how to approximate derivatives. In the same way, I can approximate d square rho to the yj, to the y square. It can be approximated as rho ij plus 1 minus 2 rho ij plus rho ij minus 1 divided by h squared. So if I put it all together, I would get that the Laplacian of rho can be approximated simply. Now you just have to add the two together, and you notice that this is the thing that is putting it together, is going to be equal to 4 rho ij minus rho I minus 1j minus rho I plus 1j minus rho ij plus 1 minus rho ij minus 1, and all this divided by h squared. And the way you can think about it is that if you have something that looks like this, it's a 5-point stencil as it's called, so it depends on 5 points. So if I want to express the derivative, the second derivative here, it really depends on the value of the rho here, 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 and here. And we give a value of 4 to this point and a value of minus 1, sorry, actually it should be minus here. That's my mistake in signs. Minus here, plus, 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 plus. So minus 4 over here, and then 1, 1, 1, 1. Or if you want to think about it as a stencil, we write it as minus 4 connected to 1, 1, 1, 1. And this, something like this, is really discretizing the Laplacian of this thing. Everything that can happen here happens inside the domain. The only thing we have to think about what happens when we get, for example, to the edge of the domain. So for example, when we are here, we can put minus 4 in here, but what happened to the minus 1 that's supposed to come over here? And that's what we're going to discuss now, is basically dealing with the boundary condition. How do you deal with whatever happens when you get to the edge of your domain? Talk about boundary condition. So this is really addressing only in this case we decided to remember that x was here and y was here. So that's really we discuss only the derivative in the y direction, but similar things will happen over here. So I'm looking basically at the second derivative in y. So d square rho to dy square. And that was supposed to be equal to, so once again, I'm looking at rho ij plus 1 minus 2 rho ij plus rho ij minus 1 divided by h squared. And now I need to go to the point j plus 1, which is this point, but it's out of my domain. So the question is, what do I do there? The answer for this depends on what is the boundary condition I have. And again, we will consider two types of boundary condition. One type of boundary condition is to say that the rho to dy on the boundary is equal to 0, or rho over the boundary is equal to 0. So, by the way, the rho dy and also the rho dx. So it doesn't matter which direction we go. This one is called Neumann boundary condition. And this one is called Dirichlet boundary condition. So now we need to discuss how to do this. And that's actually a relatively straightforward. What we do is we put a point here which we call a ghost point. So I'll use a different color for this. We call this thing a ghost point. So let's call this thing rho ghost. And I'm just going to write an equation for Neumann condition. I'm just going to write an equation for this. So if I have a Neumann condition, I'm looking at this point, which is rho ij over here. And I can say that a rho ghost minus a rho ij is supposed to be equal to 0, and that's, or divided by h, I would say, supposed to be equal to 0, and that's because basically this is an approximation for the derivative. So from here we see that in order for this to happen, I have to have that rho ghost is equal to rho ij. So I go to this point over here, and the rho ij plus 1 is replaced by rho ghost, but rho ghost is equal to rho ij. So what I get here, this thing becomes, I'll write it the whole thing, rho ghost minus 2 rho ij minus rho ij minus 1 divided by h squared. but now I have rho ghost is equal to rho ij. This minus this is giving me, sorry, the plus here, it's giving me just minus rho ij, so that's equal to rho ij minus rho ij minus 1 divided by h. And this is how this is changed. The stencil changes as I go outside. So if I go here, I don't really have a 4-point stencil, I would have a 3-point stencil. In this direction nothing would change, but in this direction it will involve only this point, and the weight will be here, 1 from here. I have contribution from 1 rather than the usual 2, and then we will work out to see what happened to the whole Laplacian as we go along. Similar things will happen in the x direction, and the rest I will just leave to the Jupyter notebook, and with a bunch of exercises how to implement also this boundary condition, which is a little bit, well, it's kind of the same, the trickiness about in the same way, but requires a little bit of thinking, so I'll let you do the thinking in the Jupyter notebook as an exercise. I hope this is helping to understand how we discretize the Laplacian over this thing, and then we will continue over the next time when we're doing the whole heat equation and propagating something over the domain as a heat